Okay, let's go ahead. So what we're gonna do, guys, tonight or today, not tonight, still in the night. We're gonna go and look at voltage drop for electrical systems. Voltage drop for electrical systems. For voltage drop, there's a few ways of doing voltage drop. We're gonna do the hands-on way. The second way is to do it is to use this calculator. Really, really handy. Very nice too. Couple of plugs and you get your numbers. Electrical Calc Pro, and a couple of hits, and you get your answer. Also, DeWalt has table 8 in it. I don't know exactly where, but I know it has table 8 in it. And Brad is going to search it for us. When we do voltage drop calculation, guys, there's a few things that we need to take into consideration. Voltage drop as recommendation in the NEC code book, not required. It's recommendation, but in the engineering community, it is required. You have to check for your voltage drop. Otherwise, your equipment might malfunction. Why do we care about voltage drop? If you have an equipment rated for 120 and you give it 100 volt, do you think the equipment, if it's not running, do you think it's going to start? Might not start. If it's starting, might malfunction. If it started, does not malfunction, it will actually run inefficient. So there's a couple of things about voltage drop, guys. You have a piece of equipment, and that piece of equipment is going to run at 120, and you went and you give it 100. Okay, you try to start this piece of equipment at 100 volt. It might not start. If it started, it might not work properly, and if it works properly, it definitely will not work efficiently. Does that make sense? The word. So start it. Number one. Number two, working properly, meaning it should do what it's supposed to do. Melt. It's not melting. It's hot, but it's not melting. You know what I mean? Or it's not working efficiently. It's not giving you the amount of heat or the amount of cool or the amount of energy that you're supposed to do. Okay, so that's the reason why we have voltage drop, because we want the equipment to work efficiently, start and work efficiently. When we do voltage drop, guys, you have to keep in mind two things. Number one, as we have a couple of formulas dear to my heart and dear to yours. I want to write them here, and you guys are going to write them for 3-phase and single phase. Let me just minimize this one quick, and then I'll go write these formulas. We'll get back to the NEC code book. We'll get back to the NEC code book in a second. Here you go. So let's just do a couple of things, and I'll get back to table 8. Here you go. So this will be unit number 8 in the NEC code in my code's book, and we're going to talk about voltage drop. A couple of things about voltage drop. Here's a piece of equipment. Come over here. This piece of equipment is rated for 240 3-phase, and the voltage system coming from this panel is 240 3-phase, 240 3-phase. But because that's what the equipment is rated for, 240 3-phase, it doesn't matter what the watt is, could be any watt, any horsepower. And because of the length of the distance from here to here, you started with 240 here, but right at the equipment, you went and you measure the voltage, you end up with 200 volts. That's what voltage drop can do to you, right? It's rated for 240. The system is 240, we should be cool, right? Except you ran a distance of 500 feet away from each other. 500, I'm just giving this example, 500 feet, and you end up with 200 volt across an equipment that's supposed to run at 240. Three things could happen. If it's a motor might not start, or an equipment might not start. Number one, if it starts, it will definitely, it might malfunction, might not give you what you're supposed to do. And number three, if it starts and not malfunction, definitely will be not efficient, inefficient. Consume a lot of power for the amount of product that's supposed to do. So that's the main reason, guys, for having a voltage drop. Most of the equipment, most of the manufacturers, most of the manufacturers give you an equipment that can work plus or minus 5 to 10% of the voltage, 5 or 10%. They take this into consideration. They say, you know, Brad, we know that that physics is physics, and we can't put the equipment right next to the panel. You have to put it further away because of the location, the function. They take this into consideration and they size the equipment to work plus or minus 5 to 10%. Does that make sense? So plus or minus 5 to 10%. So meaning you can up it up to between 5%, between plus or minus. A lot of people make them plus or minus 5, others make it plus or minus 6, 7, but between plus or minus 5 and 10%. Am I writing it right? Between plus and minus, so plus or minus 5% all the way to plus or minus 10%. Are you guys with me? This is a range. A range. Let's take an example. Let's take a voltage 240 voltage, rated equipment, rated. So a manufacturer will take the 240. This is my rated equipment, right? And I'm going to go see what's 10% down on this. What's 10% down on here's 10% multiplied by 240. What would that give you guys? How much? 216 volt. 216 volt. Okay? 216 volt. That's the 90%. That's a 9 over 10 over 100. See what I mean? Because we took 10% gotten away, so we have this is for a 10% minus 10%. The voltage is down 10%. Everybody knows what I did? The voltage is down 10%. That will leave you what? 90% of the voltage. What's 90% of 240? 216. Let's go to plus 2%. Here's a 240 rated equipment. Let's see what happens if you have a plus 10% on it. Meaning up the voltage 10%. How do you up a voltage 10%? You multiply by 1.1, right? If you got 3% raise in your salary, how much is your salary, right? 1.03. So let's say this becomes 1.1. Everybody knows why 1.1? Up it 10%. Or I'm going to get it right away because you guys good with percentage. 1.1 times what? Times 240. Who's my calculator? I'm putting grades for engagement, guys. Just FYI this weekend. So incentives. How much?
264.
264 volt. 264 volt.
249. That's right.
This sounds. Is this right? 240 times. Okay.
So yeah.
So 264. Oh yeah, because it's 240. Okay. 264. So plus or minus. So what's the difference, guys, between, can you do me a favor and find the difference between 240 minus 216? 50?
Oh, no.
240 minus 216 is 24 volt. So what does that mean? Means I can go plus 24 minus 24 in the equipment, and the equipment will, for the most part, function right. That's what most of the equipment are rated for. But remember, other equipments are rated 5%. So between 5 to 10%, I gave an example of 10%. What happens? So if the voltage here reaches, if the equipment is rated for plus or minus 10% here, and if I give this piece of equipment 264 or 216, the equipment should function okay within this range. That's what the manufacturer rated their equipment. Let's go to the code. Any questions about that? Plus or minus 5 to 10% equipment rating, 5 to 10. We call this voltage, anybody knows what this voltage is? Nominal voltage. That's the voltage nominal voltage. Everybody knows? At the source. That's our nominal voltage, the voltage that we start with. Okay. Any questions about this? It's recorded. Any question, guys? Mr. Irbab? I see your eyes are looking at me sharp, so there's a question, man, hiding somewhere. All right, let's go to the code. Now let's go to the NEC code. Let's go to NEC. If you guys go to the NEC, and I'll get you into the table that tells you a few things about feeders, branch circuits and feeders. Overconduction device. over current. Who's going to take me to services? Yeah, we want feeders and branch circuits. That's before. 210. Branch circuits 210. Feeders is 215.
So if you want to go for calculation.
215. 215.
Branch circuit feeder and service calculations is equal.
Okay, if you guys go to Article 215 or Article 2, what was the branch circuit? 210? 210. There's recommendation there about voltage drop percentage. Voltage drop percentage. And it is recommendation. Conductors for feeders as defined, blah, blah, blah. Size to prevent voltage drop exceeding 3%, the farthest. So this is in Article 215. Let's start with 215.2a. 215.2a, and actually goes all the way to A3, and the footprint note. Footprint note. They changed them in NEC 2011 now. It will tell you guys on the feeders. This is for feeders. Feeders. It says recommendation on feeders 3%. No more than 3%. No more than 3%. So 3%, the furthest outlet of the heating, blah, blah, blah. The total of voltage, feeders, and branch circuits. So if you guys go through that one, it actually divided into this. And let's just do it this way. Here's my piece of equipment. Here's the second piece of equipment. It will tell you, if you read through it, it says 3% here, 2% here, or 2% here, 3% here, for a total of no more than 5%. And what is this and what is that? This is feeder. This is, anybody knows what this is? Not this side. Let's just put the right location for it. Overcome diction device. Here's my equipment here. This is, what did we say? 2%. 2%. And anybody knows what do we call the last overcome diction device to the utilization equipment? Branch circuit. So everybody knows that it's 2%.
I'm not seeing that. I don't see a 215 to. It's on the fine print.
If you read, you have to interpret the 3%. It says no more than 3, and both of them together no more than 5. So how are you going to do it? 3 and 5. So one of them has to be 2 and the other has to be 3. It's not saying 2. It's saying no more than 3 on one of them, on the other one, but total have to be 5. So when you interpret your combo based on this, it's going to be either 3, 2, or 2, 3. Yes, sir.
So, besides prevent voltage drop exceeding 2% the furthest outlet, or is it Frank, note number 2 that we're looking at?
I am looking at 215.2a for feeders 3. A conductor for feeders as defined in Article 100, size to prevent the voltage drop exceeding 3% at the furthest outlet of the power, heating, and lighting loads, or combination of such loads, and where the maximum total voltage drop on both feeders and branch circuits to the furthest outlet does not exceed 5%, will provide reasonable efficiency of operation. They don't say 2%, guys. They tell you total of 5, no more than 3 on feeder. And if you go to the article that talks about branch circuits, which is Article 210, you'll find the same note that they will give you 3 or total of 5.
So all it's really saying is that if you have 3% on your feeders,
You can't have more than 2 on the branch circuits. Or if you have 2 on the branch circuits, you can't have more than 3 on the feeders. Am I clear, guys, about this? 2, 3, or 3, 2. So most of the engineers, here's what most of the engineers do, guys. They go by this. These engineers that I know, they go by this combo. So we take 3% on feeders and 2% on branch circuits. Okay, everybody know where we got that from the code? 3, 2. Most of engineers take 3 on feeders, 2 on branch circuits. Why? Why do you guys think 3, 2? Because what's the furthest usually? The feeders. Branch circuits are distance-wise are closer. So you can do 2, 3 though, but 3, 2. And by the way, these are footprint notes. What does that mean? They're not even enforceable. But again, the code is a minimum. We're engineers. We go much higher, not much higher. We go higher than what the code is asking for. Have we established the criteria for 3 and 2% for branch circuits and feeders? Everybody established that criteria? We established the criteria. All right, after we establish the criteria, anybody disagree with Chad? Don't disagree with me now. Let me put the article. So we got this, guys. Also another article that you need to go is 210 dot. This is for the branch circuits. 210.19a. So you don't think Chad brought this one from my basement. One, and right under 1, you're going to find footprint note number 4. Footprint note number 4. This tells you the same information. This will tell you the same information for branch circuit. So same information if you guys are there. If you read it, almost the same information for branch circuits. Anybody has an issue with that? We're cool? So we established, we know where in the NEC code talks about voltage drop. We know it's unenforceable, but we enforce it just because we're engineers. And we're going to go 3-2 because most of engineers go 3-2. Makes sense. Feeders are further. Questions? Brooks, my friend, you're so quiet. You got to say something today. It's Friday, man. No? Muhammad, how are the kids? Doing good? That's good. All right, any question, guys? So we established the criteria why we need voltage drop. Where does it talk in the NEC code book about voltage drop? Let's go do voltage drop calculation now. Anybody has an issue with that? All right, let's put the criteria. Here's a few formulas that you need to know, dear to your heart, dear to your friends Chad's heart, and the chicken hugger. Okay, formulas. Calculation. How to do voltage drop for VD. Okay, let's establish the criteria. Number one formula that we're going to use is voltage drop equal to times kill KIL over circular mil. To kill over circular mil. To kill over circular mil. That's how I always remember it. To kill over circular mil. Never goes from my. Anybody ever think of it this way? To kill over circular mil? That's
Equals VD.
not over chicken. We don't kill over anything, man. But just for that remembrance. Okay. The other formula that you can use is VD equal 2 times RIL, R-I-L over 1,000. And these two formulas are for single phase, and you can use them also for DC. If you're using a DC circuit or single phase, you can use these two for any one of these two formulas. They should come up with the same answer. Did you guys do a voltage drop calculation before with Gary? No? Okay. With Gary, a little bit. Voltage drop. Okay. So these are the two formulas for single phase or DC. Now, formula number 2 is voltage drop equal 1.73 times, again, kill KIL over circular mil, or voltage drop equal 1.73 times RIL, R-I-L over 1,000. These two are for what? Anybody can give a guess? Three phase. Now let's establish the criteria. Any one of them will do the job. Any one of them will do the job. Any one of them will do the job. Now let's say what we're talking about here. Everybody knows what 2 is. What is 2? DJ. What's 2? 2 is 2.
What's
Duh, Chad. What's K?
It's the constant for the
Constant for the material constant, the conductivity of that material, constant given. For copper, anybody remember copper? 12.9, don't have to remember it. And aluminum, 21.2, and sometimes you get them in. These two factors, guys, are material-oriented factors, depend on temperature, and they change from one location to another. For the most part, 12.9 and 21.2, is that what let's set these as a criteria. So K, let's put K for copper, Cu, what is it again, 12.9, and K for Al, let's set this one as 21.2. At least this is what our book is using. Constant given, material oriented. So if I use iron,
The book says 2.
the K will be different, right? Or steel, the K will be different. All right, what's I? Muhammad, my friend, what's I? The current. It's Friday. What's L? The distance in meters or feet? In feet. What's circular mill? The cross-section area of the conductor. Okay, everybody, we established the criteria. Everybody knows what we're talking about here.
So do we have to know?
Dividing it by 1,000.
We're coming in a second.
We have to
Did we?
divide every
Did
one.
I move yet to the red bread? I didn't move to red yet. Yes, sir.
Do we have to know all the constants? Because you're gonna change.
Memorize them? You mean no memorize them? No.
During this test, you.
They're in the Walt book. They're in the book. You'll get them for the answers. Even in then, even state exam, they will give it to you guys. Yes, sir. 12.9 and AL 21.2. Can you guys give me 1 second here?
What is it? The book says 12.2. I don't know, I always memorize this 12.9, but
Sorry, guys. I'm sorry, Mr. Erbab, what was it? KCU is for the cover, 12.9, and KAL for aluminum. Aluminium. That's what I used to call it. For 21.2. Okay? These are given. And they're temperature dependent. When the temperature change, they change, but don't worry about that one. Temperature dependent. Any question, guys, about the criteria? Write them down, bring them to the test.
So it's like, what are we writing that as? K equals 12.9?
Yeah.
And then what is the other one?
KAL
Okay.
equals
Oh,
21.2.
Page 122 in your Walt book.
Okay. Any question, guys, about the factors in the blue formula? Let's go to the factors in the red formula if there is no problem. I know you have a question. What's 2? 2 is 2, Chad. Duh. What's L? Length. I, current in amps. R is the resistance. R is the resistance taken from table. There are 2 tables. If it's single phase, we're going to be using, for the most part, guys, we're going to be using table number 8, chapter 9. So I'm going to go grab this baby here. I'm going to take it all the way here. NEC chapter 9, table number 8. For the most part, guys, we're going to be using table number 8. Table number 8, Brad, I know you asked the question is, why divided by 1,000? Table number 8 gives you the answer in kilofoot. The number that you see in table number 8, which I'm going to show you now, these are in kilofoot. So this formula, all what you have to do is just grab the number from that table, and you don't have to worry about dividing it by 1,000. Why? Because if you grab the numbers and slot this number right in here, it's already divided by 1,000. That 1,000, because the number that you get from the table is, like if you find 0.23 for every 1,000 feet, always given in 1,000 feet. Okay, so we established the criteria. We use R for DC, guys, for the most part. Later on, we can start using Z, the impedance, the impedance, which is table number 9. So can you guys write also table number 9, table number 9, table number 8 and table number 9 is where you get the R or the, which we're going to change it into Z later on. Yes, sir.
I don't understand why then you wouldn't just use the one that's always got the constant, but you don't have to, so that you don't have to go and convert to different resistances.
Good point. Good point. What if the temperature is different though? That's a key point that I always use a table, guys, because the code is set. If I don't want to worry about is this cover 12.9 or 12.1, because that 12 is temperature dependent. It depends on temperature. The best way to do that, what I would do, if I don't have the book, if I'm doing my calculation in a real project, I always use this one. Why? Because I always have my NEC code book right in front of me, and I always can find R. Always. You should come up with the same number for the most part. But R is part of the code, guys, and we always have the code, and the code is adopted, the code is approved. So if I use R, I'm covered regardless of the value of K for this particular application.
And
Not
that's almost
according to
per kilowatt.
this.
Yep, ohms per kilofoot. That's why we have the 1,000. We divide by 1,000. Yes.
Just based on the table that I'm looking at,
Yep.
table 8, my resistances of my copper based on the size of the copper is always different regardless, so how can you use constant?
Different for different conductor though.
It's copper all the way down.
Yeah, but the size, different size.
Right, but copper is copper, right?
Yeah.
So how can we use the constant in the upper?
Here, because the amp, for example, using number 4 aught versus number 1.
Okay, the amps
Yeah,
are different.
the amp will be different.
Got it.
So that's where it equals each other up. Good point though. All right, let's go to the 3-phase. What's the 1.73 and why do we have it? 3-phase, duh, Chad. What's the K? The constant, material dependent. I is current, L is length, and circular mill is circular mill. R is the same R rail, and it changes into impedance later on. Any question, guys? Any question about the criteria? Have we established the criteria? Yes, sir.
Why don't you just go to the impedance right away?
Why don't you go to the impedance right away? Good point. Why don't we go to the impedance right away? You can. In an AC, this R, guys, is called a DCR. But if you look at the values, let me step. When do I use 9 versus when do I use 8? That's what you accept. Let's just go NEC, chapter 9, table number 8, table number 9. Table number 8 is for DC. Table number 9 is for AC. Table number 8 gives you R. Table number 9 gives you Z. Impedance, give you Z. Okay? And we'll look at them in a second, guys. For the most part, if your conductors, and from statistical analysis, and if you look at this book, if your conductors are up to, so conductor number 1 all the way to number 4 aught, for the most part, R equals Z. That's why we always use table 8. If you guys look at the values of Z and the values of R from table 8 and from table 9, for the most part, up to size 4 aught, for the most part, they are kind of the same. So you can use either. Higher than that, you start getting into the impedance. And I don't want to go to the impedance because I leave this one to the commercial. Get into the impedance, and you start using Z. What's Z? I hope you learned with Gary Z. Z is the impedance. Z is the vectorial summation of the R's and the XL's and XC's, right? Vectorially added. So DJ, your mom lied to you when she told you 2 plus 2 is 4. She did lie to you, because my mom lied to me. 2 plus 2, it depends how you add them. Are you adding them algebraically or are you adding them vectorially? 2 plus 2 is 2.7 or so if you add them vectorially, right? You take 2, you square the 2, plus another 2, square the other 2, equal them, take the square root of them. 2 plus 2 is 2.8 if they're vectorially added, but 2 plus 2 if they're algebraically added or arithmetically added are 4. You guys learned that with Gary, right? That's why we have the triangle, power triangle, and impedance triangle. So that's what you're going to do in the bar this weekend. Tell them that 2 plus 2 is not 4. That's what Chad told me. That chicken hugger. Any questions about that? So up to R and Z, we're going to be using, for the most part, we will be using table 8 for this. As we go, guys, in the commercial industry, we start to talk about impedance. What's the difference? What is the difference between R and Z? R does not take into consideration the capacitance of the system and the inductance of the system. Z does. Because remember, in a three-phase, guys, there is a capacitance and there is inductance in the system. Now, what is the capacitance of a cable going through this What's the capacitance of a cable going through this conduit? Well, there's a hot, right? The capacitance is there's a hot conductor inside the conduit and a grounded conductor right underneath, a grounded surface, which is a conduit right underneath it. The two together create the capacitance, believe it or not, and there will be impedance because of leakage of current in between them. That create impedance. So, and this is the capacitance. What's the inductive reactance? Inductive reactance, as you move your conductor through the system, you loop them, you kind of creating a coil, right? Because what is the inductive reactance? It's a coil, the impedance of a coil. As you move your branch circuits and feeder up and down and over, you're looping them, right? So that creates some type of an impedance for the system coming from the inductive reactance. For the most part, we're going to assume that they're the same now and use only table 8. Questions? Camille, my friend, it's Friday, but man, it's a good topic here. I'm picking Camille today. Who am I going to pick on? Next gem. Be ready, so I can pick on you.
Are you recording?
Yeah, everything's recorded, man. It's going to be on YouTube. Yeah, this weekend. Any question?
Let me go back.
Back, there you go.
So on your red,
Red 1.
should that be RIL divided by CM times 1,000 or just divided by 1,000?
CM, if you're using the R, CM is incorporated in the R. That's why we use the R. R, if you're using R, you do not need the CM because R is the impedance of the conductor, which is incorporating the CM, the cross-section area of the conductor. So either you use CM or R. You can't use both of them at the same time. Because how do you get CM? From the conductor size. From a conductor size. What does the conductor size give you? The R. So either R rel or kill over CM or rel over 100. If they put it this way, that's wrong. And I can put my PE license, put my BE license on that one.
So you should change these R's to K.
You should change it. If it doesn't say K, I think I changed mine too. Which page are you in?
123.
What do you mean 123?
1-23.
Oh, 1-23. That's what I thought. 1-23, 1-24, 1-20. Yup, I changed VD to K. Yup, I changed mine. The first formula should be, if you guys have DeWalt 123, the first formula should say voltage drop equal 2 instead of R to kill, KIL over CM. And the second one, also the three-phase, should say K instead of R. If you use R, in page 1-23, the top two formulas instead of R, K.
On the top.
Yep, and actually the same thing with three-phase. Wherever you see an R, put a K in the whole formula here. Good grief.
For the conductor length and the conductor size one?
For the conductor length and voltage drop, also change them. If you see CM, put a K with it. Wherever you see a CM,
In the whole book.
no, in this just 1-2, 3. And the last two formulas are okay. The last two formulas are okay. Except, you see, Brad, the difference between the last two formulas at the bottom and the ones I put on the board, they don't have the 1,000. Why? Because they assume you're going to take it from the table and divide and take it as divide it right there by 1,000. Okay.
So the two on the bottom are right.
Two on bottom are right.
It's okay, though, aren't they?
Yeah.
Because of CMI.
No, they're using ours here.
But I'm gonna-
Real. Yeah. No, I'm sorry. Oh man. No, you use. Yeah, they can't be. Use put instead of put K instead of R. Instead of R, put K. Yep.
What?
Uh,
You're all
in
kids.
page 1-23, guys, wherever you see R, put a K. Okay. Wherever in page 1-23, DeWalt. Wherever you see in these formulas an R, replace it by a K. So they're giving you just the K formula.
Mhm.
There's another mistake.
K is
Thank
constant
you all.
for copper and
Yep.
R.
Shall we start taking examples?
So is it the same two as the other previous one? Was it the ones in blue?
so.
Yes, it should be the ones that in DeWalt are the ones in the blue. They're not giving you the ones in the red. If I were you, I would write the ones in the red right there too, guys. Write them separate on DeWalt.
Go ahead yet.
Don't go ahead.
Do not yet.
We'll go get coffee then. Oh, what happened to the coffee? Nobody's gonna make us coffee for you guys? And, chicken hunters and all this good stuff.
You want me to make some?
And a few, not now. Because we need to have a few examples. I'll give a break and. Okay, when you guys are done, we're gonna take an example. Did we cover this, guys, last year? Seriously, in that depth? No? Okay, that's good. So we'll slow down. Slow down. We'll slow down and we'll cover. How's the commute today?
I drove.
You drove? Ah, that's betraying your values, man.
Values, I don't have any.
He's a musician.
Cool? Everybody's cool? Move on?
Cool.
All right. Let's take examples now. We established the criteria for using. Let's take an example. All right, example number 1. We have a load.
That thing looks like it's writing better now.
Is it? Yeah. Thanks to you, my friend. And let's take a load. My load here is 3 conductors number 8. 3 conductors number 8. And they are copper because I'm vested in the copper company. And the amp of the load is 33 amps. 33 amps. And the distance, the length from here to here is 150 feet. 150 feet. The voltage system that I am taking from this is a 3-phase 208, and it's a 3-phase. I have a 3-phase load 150 feet away from a source, which is the panel, and I need to find the voltage drop. What's the voltage drop? So everybody saw the criteria, and my question is, what is voltage drop? What's voltage drop in this system? I have a load. Can you guys wake up one more time with me? When we do voltage drop, Spencer, we always use, if that was a motor, here's a question for you. If that was a motor, which full load amp would you use? The NEC code book or the nameplate? If that was a motor, which full load amp would you use? The NEC code book or the nameplate? The nameplate. Why? Why? No, the question is why? Because the nameplate is the actual current that's going to be going through the conductor. The NEC code book is artificial value. It's already overrated, means it's pumped up. It's not the real value that's going to go through the conductor. When you do voltage drop, you need to really know what is the amount of current that goes through this conductor, the actual value, the actual value. That's what's going to cause the voltage drop. Everything else is going to be safety. These are safety factors. Okay, so the actual, you're going to use the actual value. 33 amp, these are the nameplate. Can you guys use this as name plate amp? Nameplate amp. Not modified, not continuous, non-continuous. I don't care. I'm not sizing conductors. I already sized my conductors. I want to see is my conductor now after, if it was a continuous, number 8 will be sized based on continuous. Then I check, I size it based on continuous, then I check it for voltage drop. All right, let's do a voltage drop. Example, which example number? Example number 1. Okay, VD equal what? 1.73 times voltage times current, not voltage, duh, times in this case, I'm going to use, I have cover, I'm going to use, you know what, I'm going to use KIL, K-I-L over a CM, over CM. I will use KIL over CM. Do you have a problem with that? Chad is having an attitude today. 1.73 times, what's the K for copper? Established it. 12.9. What's the current, the full load current that's going through this conductor? Not how much current the conductor can carry. What's the full load current that's going through the conductor?
Where did you get the 12.9?
12.9 is assumption from
That's what's constant.
the books, a constant, constant from the books. And what's I? 33 times, what's the L? 150 divided by, what's circular mill and where do I find it? All right, let's gonna go to table 9. Oops. Table, are you there? Where's Chad? There you go. Okay, here's table number 8, guys. Table number 8, I'll get back to it. Table number 8, let me just move it up a little bit so I can see. Let's go move it up. I'm going to go all the way up to table number 8. Here you go. Now, table number 8, I need solid or stranded. It's 3, if it's always 3-phase, guys, assume it's stranded. If it's especially with 3-phase. But I have to tell you that. It's stranded. I'm going to say stranded. And here's number 8. Here's number 8. Can you guys see number 8? Here's the circular mill for number 8, right? Here's the circular mill where I found circular mill for number 8.
Is that the solid?
I did the solid. What did I told you guys stranded? Here's the stranded. How do I know it's stranded? Because it has a number 7 here, meaning 7 strands. And where's the circular mill for it? It's right here. Here's the quantity. Here's the circular mill. Here's the conductor size. Okay? And later on, so that's where I'm going to be getting the 16510. Okay? Later on, guys, when you use the DC, here's the DC resistance for cover. Your assumption is always uncoated for cover unless you hear otherwise. Here's the assumption, uncoated. So if I want to find the resistor, which I don't need it this time. If you are in England, which one would you use? Ohm per kilometer. If you're in America, like we are, you're going to have ohm kilofoot. So where's the ohm kilofoot? Right in here. We're not using it for this example, but this one obviously drop this one from your calculation. So that's where you're going to be the default. Uncoated ohms per kilofoot, and that's where the 1,000 Brad came to be in my equation. All right, everybody knows how to use this table? Yes, Chad? Don't yes. Ben?
Yes, Chad.
Yes, sir.
It's worse than his chicken, man. Okay. I'll take you to the other side, the aluminum, in a second here. But any question about the cover, guys? Any question about the cover? All right, let's take this one. take a snapshot of it. I love technology. And I'm gonna go
When are you gonna do it on the yellow calculator?
a yellow what?
On the yellow lid? When it's done?
1 second. What is she talking about? There you go.
Control calculator.
Oh, oh yeah, you mean the calculator? Oh yeah, we can test it on the calculator in a second. When we're done, we can. Okay, what's the circular mill was?
It's-
I'm gonna say strand. In this case, it really didn't matter. I'm gonna say it's stranded, and it was 16, 5, 10. Okay, who is the gentleman or the lady who's gonna get 10 out of 10 in classroom engagement? He jumped in, man. How much? 6.69. What's the unit for 6 points? I need another lady or gentleman who agrees with. Agrees? Yep.
Yes.
Okay. What's the unit for this? Percentage or volt? Volts. Very important. This is a volt. Now my question for all of you, based on the criteria that we established with the NEC code book 3.2 or 2.3, is this good, bad, or ugly? Can you tell just by looking at it if it's good, bad, or ugly at this moment? Can you? No. So what do you need to do to discover if it's good, bad, or ugly? You need to divide it by the mother voltage, the source voltage. So let's go divide this by the source voltage. So 6.69 divided by, what's the source voltage? Not 120. You're going voltage drop in a three-phase. You're going phase to phase, not phase to neutral, phase to phase. Okay. Who is the gentleman who's going to get 10 out of 10 this classroom engagement?
2%.
Huh? 3%? Even?
3.2%.
Now that's a different story now. So 3.2%. Is this good, bad, or ugly? Remember, what's the criteria? We need 3
Or better.
or less. 3 or less. So that's supposed to be, it's not less than 3. What did you come up with, Spencer?
Well, here, okay, voltage drop is 6.69.
Mm-hmm.
So I took 208 divided by 0.03 and I get 6.9, so we should be in the clear. See how, that's one way to go about it, man.
Say it again.
3% of 208,
3%?
6.9.
Yeah, 6
And
point.
we came in at 6.6.
Multiply 208. Multiply 208 times 0.03, not divided.
Okay.
3% of 208 is 6 point.
What's 3% of 208? Yes. What's 3% of 208? 6 point.
6.24.
So it's less than what that. So this is ugly. This is bad.
3% of 208.
Not acceptable by Chad or the NEC code book. NEC. Remember, the NEC is a recommendation for this. Okay, now we know what the problem is. Here's my question for you, buddies. I'm going to go size a conductor that can actually get me to meet the code. I'm going to go, you're the engineer, you're going to resize this. I'm going to go resize the system to get me a conductor. The answer, Brooks, would be easily, well, Chad, go to higher. What's the higher than 6? Higher than 8? 6. Let's go to 6. But let's see, let's do the calculation and see how much would it take us to correct this problem. This is a problem. I need to keep it below 3.
Can we do it on the yellow calculator right now? Finish up?
Let me just finish. Can I finish that one up? Okay, and then I'll give you a break and then we'll do it. All right, so everybody knows what we did. We find the voltage drop. We need to go, we have an issue. We need to correct it. Okay, move on here. Go correct. All right, so what do I need? The problem becomes the same problem, guys. 33, except this time I need the conductor sizing copper. The same distance. What was the distance? 150 feet. Same distance. And the voltage is 208 and a 3-phase. And the load is also 3-phase. Can I feed a single load a single phase 33 amps from a three-phase 208 system?
Can you repeat your statement?
Yes. Good point.
Yeah.
Can I feed a single phase load, 33 amps, single phase, from a three-phase system 208? Can I? Why not? Yeah, you're just taking two phases. All right, so this doesn't have to be three-phase. In this case, we assumed it was three-phase because of our example. Let's go correct. How do we correct? Correct means, here's a formula when you transpose the voltage drop equal 1.73 times, this is a KIL divided by CM. When I correct, and I hope your algebra knowledge is good enough to flip these, I want to find CM this time. So 1.73 times KIL over voltage drop. Everybody knows that this is equivalent to this. Otherwise, you're going all the way back to Mr. Ryman. I'm not going to sit here and solve equation, algebraic equation and all stuff. Eric, my friend? Cool, right? Not biggie? All right. So what did I do? I flipped the formula. I need to find the CM. What's the CM? CM is a conductor size, guys. All right, let's plug in. 1.73 times, what's K? 12.9 times, what's I? The same I, Chad, duh. What's L? Same L, 150, divided by, what's the voltage? What's the voltage drop? I need to meet, which voltage drop do I need to meet? I need to meet the 3% voltage drop. The value, that voltage drop value here is not a percentage, it's an actual volt. So how do you convert 3% of the system 208 into volts? You multiply 0.03 by 208. So that's where this came to be, which is 0.08 times 208. Mistake number one, Spencer, on the test. A lot of people come right here where the voltage drop is, and you know what they do? They just put 0.08 and they stop.
It's 0.03.
Why did you get me 0.08?
I just told you it wasn't 0.08.
Okay, it's 0.03. So mistake number one, like other than mistake Chad, 0.03. Other than, so the mistake number one is the people who put 0.08 and they forget to multiply by 208. 0.03 and they forget to multiply it by 208. Okay? So you have to multiply the percentage by the voltage to find the actual volts. Who's going to get 10 out of 10 in the classroom engagement?
17,
17? 17703, right? 177. What's the unit for this boy? CM. What's the unit for this boy? CMs. Everybody, I need two gentlemen came up with the same answer, or a gentleman lady. Yep, good. Approved. Okay. Now what the heck is this conductor? I have no idea. Okay, then next you're going to take this 17703 to our Bible, NEC, under which table? Chapter 9, table 8. And what would that get you, my friends? You could have told me that before I went and did the whole mess here, right? Easily. So that will get me number 6. Except I proved it here. I proved it. I could have easily looked at it and say, you know what, throw number 6. That's what they do, number 6. Now I proved that I need number 6. Any question, my friends? Any question? 5 minutes break? We'll reconvene. No, okay.
That's fine.
I tell you, that technology. Okay, so we have a 3 horsepower motor, 230 single phase, 300 feet away from the source. The source is 240 3-phase, 243 phase panel. Everybody knows what, when I draw this, it's just representing 2 wires, right? Can I feed a single phase load from a 3-phase system? No problem, bring it on, Chad. All right, so we need to find the conductor size that meet the criteria. The conductor size that meet the criteria. Well, before we do anything, let's go just size the conductor based on the NEC code book. Just size the conductor. It's a motor. I taught you guys how to size the conductors for motors. Before we look at the voltage drop, and then we go size based on voltage drop. When you are faced with a situation like this, guys, first you size it based on the NEC code book, then you go check if you have a voltage drop problem or not. Looking at the distance, I know most likely I will have a voltage drop problem. So let's go size it first. So first, size based on continuous load. It's a continuous load like motors. So how do you size a conductor for motor? Number one, the 3 horsepower, you need to find the full load current from where do you go? 430.248 table. Everybody knows how to go to table 430.248.
We do, but we don't know why we're using that now, so.
Ah,
Because we're sizing.
good. Chad, just a couple of minutes ago, you told us we used the full load, the nameplate of the motor. Do you see any nameplate there? Did I give you a nameplate? Do you see any nameplate?
Why can't we do the
Do you
H?
see? No. So what are you going to do?
Why can't we do H?
You don't have the nameplate. That's technically you have a motor. That's what you're going to face as a designer. What you know about the motor is a horsepower motor, and you have no idea what the nameplate is yet. So what do? You use what the code tells you.
Why can't we do?
Okay? Am I clear, guys? I'm trying to get you in scenarios where real scenarios. You don't have a nameplate for it. What are you going to do? 3 options: go to the bar, get drunk, and cry.
That's the one that we all prefer.
Refer. Okay. The second option is
Why
go
can't-
to the NEC code book.
Why can't we do the HP times 746 times volts?
Okay. Times. Continue. Divide by. Continue.
Divided, 208 times.
Times will continue. Continue. Efficiency and power factor. Do you know what the efficiency and the power factor for these?
Oh,
3 horse times 746 divided by your voltage.
Again, continue. You can't do that. You still have to have the power
Yeah.
factor and efficiency. Do you know the power factor and efficiency? See, guys, why you can't use that? Good points, though. Ben,
It's 9.6.
it's what?
117 if you go
Oh,
by
I thought-
the table.
By the table, it's going to be 3 horsepower at voltage 240 or 230. What's the full load current? 17? 17 amps. Thank you, my friends. 17 amps. Let's go size it based on motor sizing.
Wait. Sorry, I don't get that.
We went to,
It's a single phase motor.
oh, single phase.
Okay.
You're looking at a 3-phase. It's a single phase motor fit from a 3-phase system. Single phase motor fit from a 3-phase system, guys. That's okay. You can do that, right? No problem. So now 1.25 times the 17, what would that give you? Who's gonna get 10 out of 10 in engagement? And then you say, Chad, you want A's. What?
21.25.
How much?
21.25.
21.25, okay. And then, since it's a motor, you take 21.25 to where? 310.16 under which column and why?
49.
Because they're motors. And what would you get? Number? Under 75. Number? 12? 12. Number 12. Why are you emailing me, Mr.
I didn't. Oh, 35.
Yeah. Number 12. You can tell Chad is edgy today. Any question, guys? So that's sizing based on normal sizing, right? Not taking into consideration that we have a voltage drop problem, right? We haven't sized based on voltage drop. Yes, sir.
why isn't it 3 phase versus you're putting a single phase on?
Because the load, you go by the load. Look at the load. 3 horsepower, 230 single phase.
Right.
Yeah. You do all the time. You have a single phase tied from a 3-phase system. Not a big deal. Any question? Good question though. For a Friday, especially. Any question, my friends? Any question? Thank you, DJ.
Yeah.
You got your 5 out of 10 engagement.
Yeah, but I asked a question. I asked a question that puts me at another 5.
The coffee will give you 5 by itself, huh? Any question, guys? So we size it based on just a motor with no voltage drop problem. Let's go size it if we have a voltage drop problem, which we think we do, because it's anything, guys, higher than, if you want to know you have a problem or not, you start getting higher than probably 70 to 100. I would say 100 definitely you have to do a voltage drop calculation. Feeders or branch circuits, 100 or higher, you got to check always voltage drop. Okay, so we got this one. Let's go size now. Everybody knows what we're doing. We size it. We need to go size it based on voltage drop, because we think we have a voltage drop problem. All right, so sizing based on voltage drop. Here's the formula. Circular mill equal, it's 2 rel RIL over 1,000. Why did I choose the rel? Because I know the code. I have the code. I don't care about the keys. I want to use the, why did I use the 2, not the 1.73? Single phase. Why did I use rel? Because the code says the form, I'm going to get my info directly from the code. All right. Why did I flip this thing? Is this, no, I'm sorry. This is not the right formula. This is not the right formula. Let me just write, first voltage drop equal to rel, RIL over 1,000. I need to find the conductor, so you're going to flip this. It becomes R equal voltage drop multiplied by 1,000 divided by 2 IL. Right? Everybody knows how to flip the formula? Shall we send you back to Miss Jericho? No? Okay. Then equal, so I need to find now, look at what we're going to do. I want to find R, and guess what I do? From R, I can go to table number 8 and size based on R and find the conductor. Genius, DJ, right? Okay, what's the voltage drop acceptable in a feeder? 3%, so this is going to be 0.03. What's the voltage system? What's the voltage system? My voltage system is 240, the system? 240, the system, 240. Multiplied by 1,000, don't forget the 1,000. Divide everything, this is a 1. Divide everything by 2 times, what was I? 17, what was the distance?
300.
300.
You need to put the 1.73 in here because it's a 3-phase or 240.
The load is single phase. You go by the load. Remember, the load is single phase. We're caring about the single phase load. Yes, the system is 3-phase, but the load is single phase. Good point, though. Okay, who's going to get 10 out of 10 classroom engagement? Grade seems to work. Steve, what do you want now?
Got a number, but I think it's wrong. 701.
It's going to be a small number. It's going to be a small number. Point
701.
706. Anybody came up with this number? It's not. You're not wrong. Why? You're sizing. You're finding the resistance. You're finding the resistance. For everyone, you're finding the resistance. Right? 0.706. Now let's take this one to table. Which table? Table number 8. Let's take the 0.706 to chapter 9, table number 8. No? I'm sorry, which?
Well, your voltage drop is 3% of your system, so it's gotta be times 240.
Are you guys in the table 2.8? Table 2.8. Table 8. Where's what type? Which page is table 8?
681.
681. 6. Okay, what anybody came up with a number? We're gonna go under impedance 681. There you go, I was close. You're gonna go under impedance, under copper. We're assuming it's copper, uncoated. So 0.706 under uncoated 0.706. How about number 8? Did you guys find that one? Let's go do it on the code. Let's go open the code. And because you guys are okay, went down here. Here's my excuse me, here you go. Here's my code. I'm gonna go and find an impedance that's an impedance. Remember the impedance that I'm looking for, 0.706. So I need it's a conductor that can have an impedance this value or higher. So what would that be? This value or lower, what would that be? The conductor 0.7. Oops. So that's no. I don't want that to happen. One more technology. Beautiful when you. Oh, you close it. Page 681. Let's see. There you go. No, is that 681? It didn't give me a 681. Chapter 9 table. Yeah.
Why didn't we just use the conductor size formula instead of going the roundabout way?
You can. You can, no problem. You can. Except the code, table 8. The code is what you always have in front of you. So what did we say we picked up number 8 because this one, and what was, can you give me the impedance that we had? The 0.706. So what you need, guys, you need a conductor, you need a conductor that has this resistance or no. That's the challenge. Or less. A conductor has more resistance will give you what? More voltage drop. You need a conductor that can give you this resistance or less. So 0.706. Which one will give me less than 0.706? Less than. Keep going. 0.06. Which one? Number 6. Number 6. Are you guys with me? Everybody knows why. Because you're right. When we're sizing conductor, you need a bigger conductor. But when you're looking at it from a resistance point of view, you need the one that's smaller resistance. What does smaller resistance mean? Bigger conductor. See how we look at it from a different angle? Bigger conductor, small resistance. But if you're looking for a small resistance, that's give you the bigger conductor. So then your conductor would be number 6. Why copper? Why uncoated? Because default copper uncoated. And Brad, do you see now why I put the 100 in the formula? Because when you do the R, all what you have to do is just look at the numbers. So my conductor, the 1,000. Did they say 100? Oh, I missed just one digit. 1,000.
It's not very important. You know, someone with natural 10.
Okay, everybody saw how we got that? Well, the number that we got there is 0.706. Now we're going to keep looking right in here. We're going to keep looking at this column until we find a number smaller than this number. We need to look at a number small or less. Can you guys write this down? Or less. Points are We're going to find for R equal 0.706 or less, not more. So, can you guys see that's this or less is number 6. Now we went, Mr. Boo, my friend, we went from number 12 all the way to number 6. Why? It's 300 feet. It's a long distance. 300 feet is a long distance. Can you run 300 feet 5 times? I can. When I'm not full though. Okay. There you go. Got that one captured. We go back into where we were. Questions? So what was the number then? Number 6. How many conductors? It's a 240, most likely, no neutral. What do you get? What do you get? 2. Any question, guys? Any question?
I like it when everything works out, Chad.
Perfectionist. Who's perfectionist here?
So it's easier to use it. Because you don't have to cross-reference it. Still get the same answer.
Use any formula, what? Example number 3. Jim, my friend, we're good? Bill, my friend, are you good? I like your hat today, man. All right, let's go take one example. So we size the conductors. We size the conductors, my friends. Come on, move. We size the conductor. We have the size conductor. We size the voltage drop. So we have conductors, voltage drop. I want to take an example about amps. It's not commonly used where you have to find the amps based on. It's not commonly used, guys, that you can find the amps based on a conductor from the formula. But let's take one example. Usually, either you're finding the voltage drop or you're finding the conductor size. That's what the two things normally what we do as an engineers. You have the conductor, you find the voltage drop, and you discover that you exceeded the allocation of 3% on feeders, and then you go size the conductor based on voltage drop. That's what we normally do. Well, what I'm going to do right now is not commonly used, but sometimes. Example number 3. Example number 3 is we have a lousy designer, like my friend DJ, for example. Sorry, DJ, I'm going to pick on you today. Lousy designer DJ. He went and put 3-aught aluminum, 3-aught aluminum conductor, okay? And he pulled the 3-aught from a system of, let's make it 3-phase, 480 volt, 3-phase. The system is 480 volt, 3-phase. And or let's, so that's the system. Let's put the load here. This is just the system here, overkill protection device here. Let's put the load that we're pulling out of this individual. Let's use a load that makes sense here. Based on, what do we see, 3-aught? 3-aught. So our load was, say, 120 amp. Our load was 120 amp. It's a 3-aught. Okay? 120 amp. And that's where the load was. And everything was okay and everything up and dandy. Then they decided to move the machine. And they want to move it away. When they moved it away, it became, the distance here became 400 feet. They move it away 400 feet. 400 feet. And what I need to find is, can I still take 120 amps out of this conductor? Can I still tie this machine that needs 125 out of this conductor? The question is, can I still connect 120 amp machine to the feeder after moving it moving it to 400 feet away from source. Can I? May I? Should I? So we need to find the amps. The load is 3-phase. The load is also 3-phase. It's a 3-aught. Let's make the 3-aught. Looks like a 3. Kind of odd. Okay. Everybody knows what they show. It's not 3-aught, no?
Doctor,
I'm close to
your handwriting is.
3-aught.
Ran
Chicken
ISIL.
scratch.
Can I still connect the 120 amp machine
Ran
to
ISIL.
the feeder
And chime.
after moving it to 400 feet
Fender,
away from the source?
Alter, roving it, TV 400.
TV.
Yeah, it looks like TV.
Is that
Yeah.
Read it again.
Ran ISIL, Ron Rect, 120i, M chime, 212 Fender, Al 12,
Okay,
roving.
I'm not gonna waste it. Do it again. Here's the formula. We need the formula. Voltage drop equal 1.73 times. We need to use rel. R I L over 1,000. So, based on this criteria, guys, based on moving the load, the 120 amp load 400 feet away from the source, can I still connect that load to the source? What do I need to find then? Amp. I need to find amp. So I'm going to transpose this formula into I equal voltage drop times 1,000, divide this by 1.73 because 3-phase, and I and an L.
Moving time just times out. You can have the
And of course, the eyes can't be in 2 locations, so what do you need to do? Not listen to Chad and just put the L here. Thank you. All right, let's throw the equation. It's a 208 times 0.03. Why 0.03? Times 1,000. Why 1,000? Formula, Chad. Divide by 1.73. What's the length? 400. Did we miss anything?
Yeah, you want your R out.
I left my R out of the equation at the top. Thank you. My R should be
1.7
in the bottom.
times out.
I left my R. Thank you, because my R is going to jump into the bottom.
What do you have 208? That's a. Oh yeah.
The voltage is 480. I just stuck with the 208. 480. The desk is still stuck with the 208. 480 times 0.03 times 1,000. Divide by 1 times the R. What's R? I need to go find R, guys.
21.2.
So R, let's go find R from right here. I need to find R. Where do you go to find R? Chapter 9, table 8. And what's the conductor size? 3 AL. Don't forget 3 aluminum. What was it? For aluminum, not copper.
Okay. 1, 2, 6.
0.1, 2, and 6. That stuff. In there. So 0.126. Anybody? I have 2 gentlemen agrees on 0.126. Okay, so that will be times 0.126. Okay, did we miss anything? Ryan, my friend, I have the voltage right the second time, not the first time, times 0.03 times 1,000 divided by 1.73 times 400, and we got the R the second time right, 0.126. I need 2 gentlemen or a gentleman and a lady to agree. How much?
165.
165?
Yeah.
165. Interesting. So we got one false up. Okay, so everything 165 amp. 165 amp. Can I still connect the 120 amp then to it? Why not?
Because it's got more amps.
Yeah. It got more amp capacity. Did we do everything right, guys? My amps, if you guys go to 3-aught under normal condition, how much 3-aught under normal condition can carry? 310/16. 3-aught under 310/16 under normal condition. 3-aught aluminum, 155. Can carry 155 under normal condition, 155. See it? And I was loading it to 120, so it was underloaded to start with. Can you guys see that? Why we came up with this? If you go to table 310/16, 3-aught under normal condition aluminum can carry 155. So this can carry 100 normally, 155 amps normally. And I was loading it with 120, so it was underloaded. It was underloaded to start with. It was underloaded. That's why we're okay, because it was underloaded. Does that make sense? 3-aught normally can carry 155. I was putting it at 120, only 120 carrying out of it. So when I did all my calculation, I ended up with 165. 165. Now here's my question for you guys. Can you take 165 out of number 3-aught? Even though the voltage drop says you can go 165, can you get 165? Are you allowed to get 165? No, because 310/16 governs. No matter what you do, no matter what your voltage drop calculation come up with, you cannot exceed what the conductor can carry under table 310/16, 310.16 under whichever category, 60-degree category if it's that conductor under 60-degree, or 75-degree if that conductor is more than one. But we did the calculation right, guys, right? Everybody? Okay, so we just end up, our conductor was big to start with, so we don't have problem. So what happened, guys, then, say I came up with 100 amp, then I have to go, my machine cannot be hooked up to the same conductor that was feeding it to start with. So you have to go up your conductor. That's a situation where you can use the amps. You need to find the amps. How much amp can I get out of this conductor? Because most of the time we don't do it this way. Most of the time we size the conductor to feed the amps.
So based on that, we would need a 4-aught?
No, based on that, we're okay. Remember, what governs is the load. You're going to ask yourself, my load is still 120. Can I still feed it with this conductor? Yes. I don't need to go up or down. Can I still feed it with this conductor? Yes, no problem. Just to give you an idea, let me just do that one quick. What's the voltage drop based on this criteria? If you take aluminum, I have copper, I have aluminum here, set mine for aluminum. If I take the voltage for 80 volt, and the current, what was the current? 120 amp, and the distance was, or is, 400 length. My voltage drop, the percentage, guys, based on this criteria that I'm looking at, I just did the voltage drop calculation. Just this, find the voltage drop. I have 2.8% voltage drop, 2.8%. I'm okay with this value, 2.8%. I don't have problem. See what I did? Forget about everything else. Find the voltage drop for this problem. 123 phase, 3-aught with a voltage of 4.8. If you do the voltage drop on this problem, it's 2.8. Is this a problem, percent? No, we don't have a problem. And that proves it. I don't have a problem. Any question, my friends? Before you graduate from here, you're going to get yourself one of these babies. One more problem. and then we'll call it a quit. Sorry, Bob.
Yeah.
Good?
Yeah.
That's good. Let's see what. Take a quick question here. So, I'm sorry. Let's take and I'll take another example because about the fire pump another time. In the fire pumps are special. They allow them to go dip 5%. Fire pumps. They allow them to dip 5%. Okay. Let's go size a conductor. Fire pump. Fire pump. Which article is article that talks 690. 695.7. 695.7. 695.7. NEC 695.7. All right. If you guys go there, it tells you the voltage, acceptable voltage drop when these boys are 5%. No problem. Dip it. Why? Because if you have a fire and you're fighting it, do you really care about the voltage drop? You have the fire raging in your building, and you say, "Oh, no problem. Drop the circuit that feed the fire pump because we have it's not working efficiently." It's the least of your problem, voltage drop. So they allow you to go 5%. So let's go size a baby here. Here's my baby here, and I'm gonna go size. This is a 30 horsepower. 480 volt, 480 volt, and my question for you, and so my question for you, gentlemen and lady,
Is it 15%?
15 for dip.
Oh, okay.
Dip, there's dip and drop. Dip, when you start for momentarily for 10 seconds, you can dip the voltage down to 15%, just for 10 seconds. Drop means constantly. Constantly, the voltage can constantly be 5% less, no problem.
This is voltage drop.
Is it?
605.7 says voltage drop, voltage at control line terminal not.
The voltage at the line terminal of a controller when okay, the lock rotor must not drop more than 15%.
Under motor
Motor
starting
starting
conditions.
Yeah, that's what I thought. That's okay. The starting capability 15%. The drop is 5%, right? That's what good. Thank you. Yeah, it's confusing a little bit. 5% constant drop, 15% momentarily drop or dip, they call it, for the start only. Okay, let's take this scenario, guys, and I'm gonna go. Here's the distance. I want to, because of whatever criteria here, I have to put this one at 350 feet away from the source, and my source is 480 volt. My source is at 480 volt, and I need to size the conductor that can meet. I need to size conductor size. I need to size the conductor under these criteria. The fire pump need to be moved away from the junk and put in one area, and end up 350 feet away from where it should be, we're closer to the source. So I need to size this conductor based on this criteria. Anybody has an issue with that? No? I thought so, guys. All right. So let's take, the first thing you need to do is you take the full load current of this boy from 430.2 48 to 52, I want to say, table 252, the full load current under voltage 480, right? Table 252, I believe.
Oh, there isn't a 252.
Oh wait, it's three phase. Right, 252? 250? 250, that's 250. I know one of us is awake.
It only goes up to 251.
250. Okay. All right. What's the full load current? 40. I need another gentleman or lady to agree. 40. Agree? Okay. All right. So that's a full load current. Then we need to do the calculation now. Why? If I know the nameplate, guys, I would use a nameplate. No question asked. Use a nameplate if you know the nameplate. All right. So let's do the calculation. I need. Here's the formula. The formula that I have is voltage drop equal 1.73 times rel RIL over 1,000. You can use a kill too. Can we use a kill this time instead of rel? You guys want to use the kill or the rel? Kill, because whoever use it. Let's use the kill, just because you're my friends. So 1.73 times kill, KIL divided by 1,000. The conductor that we need is copper. We need a conductor, a copper, no, 1,000 over CM, sorry. Circular mill. So we need to flip this formula, like you guys have done many times in the past. Flip it. It becomes 1.73 times K times I times L divided by voltage drop. Let's start. 1.73 times, what's K? K is copper, 12.9. Why copper? I decided I want to use copper with the fire pump, definitely. 12.9 times I, what's I? 40 times, what's the L? 350 feet. Divide everything by, what's the voltage drop acceptable by this motor? 5%, not 3%, Brooks, my friend. And you multiply this by the mother source voltage, the grandma voltage, 480. And that will get you a healthy, equal, healthy,
13,055.
how much?
13,056.
13,056. So 13056, right? Two people came up with the same answer. 13056. Come on, guys. Classroom engagement is coming.
Yeah.
Good. Okay, so that's no.
Yeah, actually got different too.
I got 1301. Yeah.
That's what I got, 1301.
13.
118.
13018. Who gave me the first number? Minus 2 points.
No, that's okay.
13018. 13018, right? We have 3-4 gentlemen with ladies. Agree with that? All right. So what do you need to do? Can you go buy yourself a CM like this? They'll laugh at you if you go to Home Depot or Vikings or anybody to asking for, can I have a 13,000, 1,800 CM? They say, which planet do you live on? Okay, so we need to go find yourself, convert this one into a language that we can use. I'm gonna just for the heck of it, I'm gonna put my conversion here. So 1308 CM. Which table are you gonna go to? Table number 8, chapter number 9 in Mr. NEC. What do you get? What do you get? 8. I have 2 gentlemen agree on number. Now, Brad, you're gonna go 1308 or higher. This time higher because we're not looking at resistance. So you need to go to find yourself 1308 or higher. So it's number 8? Yeah. Number 8. And don't be scared, guys, that number 8, that's small. Because remember 2 things. It's the voltage is 480. At 480, the voltage 480 has a lot of momentum to drop voltages. Huge voltage. That's why number 8 sounds, wow, it's long distance for number 8, right? But the voltage is huge. If you dump the voltage to 240, that will you double the conductor size. So number 8, right? Now, this is number 8. Now let's go find, normally, if we don't have a problem with voltage drop, what size conductor should we or can we use if we're not using, if we don't have a voltage drop problem? Okay, I'm going to do it and then we'll let you guys go eat. Because I don't know, Fridays people get hungrier. DJ, are you okay?
Yeah.
Scratching your head like my daughter when she doesn't know something. She scratches her head right in this corner.
Looking at the formula.
Still get you 5% man for doing copy at least. And another 5% for participating. That's
Well, 10 for say a question.
okay.
Yeah.
2 extra points for chicken too. Muhammad, my friend, any questions? No? Jem, Eric, Camille? Good. Bill? Good? You can tell Chad enjoys, man.
No.
Sorry, Carl. Okay, let's go to the other one. Can I move? Let's move. Do we have option, Chad? Move when you want, huh? Okay, let's size it normally. We don't have a voltage drop problem. We're just we're just 50 feet or less away from where we are and we're good to go. Okay, normally we size it normally with, don't laugh about my handwriting again, without voltage drop a problem. Now this is a problem. Oh, this is a problem. Now this is a good problem. How is it a good problem? Can you read this, Brad? I'm not going to rewrite it.
I've been without PD for my whole life, so.
Okay. Because they're scared. All right. Normally, without voltage drop problem, just 50 feet away from us, 70 feet. We're okay. Let's take the 1 point sizing here. So let's take 1.25. Why do you think 1.25? Motors are considered continuous load. The full load current was 40. What would that give you? 50, 50? 50. Yeah. Another German agree? Or lady? Okay. Then what do? You take the 50 to where? 310.16 table. Under which column? 75Y. Motors. What do you get? Number 8. AWG. What was the size that we came before? Number 8 too. Number 8. So we're still good. But here's why we were good. I want you guys to, here's why we're good. Look what we pumped the voltage. We pumped the voltage 125% here. That's where we came up with number 8 too. So we're still good. So number 8 could have gotten us there even without the voltage drop problem. Number 8. Why? A lot of you say, Chad, gosh, why? Why do I have to mess? Remember what we pumped in here, guys. We increased the 40 by 25%. We pumped the conductor size by 25%. But when we did the voltage drop calculation, we did it based on what? Only 40. Do you see why we came up with the same number? Some of you were confused. Why am I coming? Because we sized based on 25% extra amps, which does not exist for safety. So that's why you came up with okay number. Had you come up with a number here, number 6, which conductor are you going to use? The largest one. If this calculation came up with number 6 and the voltage drop calculation came up with number 8, just flip it. You will use the calculation that comes up with the largest number. So you do, guys, we do 3 calculations for every load. We should. Number 1 calculation based on normal condition. That's called normal condition. Calculation 2 is based on voltage drop condition. Calculation 3, which you guys have done, but probably you don't know that you have done it, based on bundling and temperature. What if I have a temperature issue here, or I have a bundling and grouping the conductor in a different temperature than normal temperature. These three calculations, you do them separate calculations, separate three calculations, and you pick the conductor that can give you the largest size conductor. You pick the calculation that can get you the largest size conductor. If you remember this, Brad, you would never have problem with sizing conductors anymore. And if you do, it becomes your problem later. Any question, guys? Any questions? Spencer, my friend? Too much for a Friday? Weekend, you'll get over it. Two things left in this chapter. We'll talk about them next time. Number one is voltage depth. We're going to size for the fire pump voltage depth. We'll do same calculation, guys, except for the locked rotor current. Locked rotor current is a fancy name for the starting current. Voltage depth based on locked rotor current, very easy. And number two, everything that you've seen, that beautiful stuff, anybody can tell me what's the assumption for everything that we've done so far? What was the assumption? There's a source, and there's a load, and in between them is a cable. That's assumption. Look at the real life situation. Here's a source, right? That's the source. Where's the load on this circuit? Show me the load on this circuit. I'll just stand up. Where is that? Show me where it's exactly located. Here, one more time. Where's the load on this circuit? Everywhere, Chad. Is it here? Is it there? It's scattered everywhere. Okay, Chad, then how far is the scattered load from the source? Is it 10 feet, 20 feet? Which one are you going to measure? 2. That's a real situation where this is easy calculation if you know that your load is located in one area, summed in one area, and your source is another area, and in between them a distance. If your load is scattered, as in parking lot lights, you're going to do a voltage drop on parking lot lights. Which light are you going to go to? Each one of them is probably 50, 60, 100 feet away from the other, right? Which one are you going to take? The one that's 50 feet away from the source, or the one that's at the end of the line, which is 500 feet away from the source? We're going to do this next week. Okay? But if the load is summed in one area, no problem. Calculation is really easy. When you get into a bigger conductor size, we start, guys, using impedance. We'll do it next quarter. We'll use the impedance versus the resistance next quarter. All right, thank you for listening to Chad.